So finally, I'm going to do an example that shows how to apply the simplex method when you don't necessarily have an obvious choice of basic feasible solution to start off with. So this is called the two-phase simplex method. So I'll illustrate the idea with an example. So this is following along with 16.4 in the textbook. So this time we want to minimize a function subject to these inequality constraints. So always the first step is to write it in standard form. It's nice because it's already in minimization form. So our standard form is going to be minimize 2x1 plus 3x2. Subject to, this time we have greater than or equal to constraints. So we're going to replace 4x1 plus 2x2 bigger than or equal to 6 with 4x1 plus 2x2 minus x3 equals 6. And x3 is going to be positive. Right. And similarly for the next inequality constraint, we're going to replace x1 plus 4x2. Whoops, I copied the problem wrong. This is a 12. So x1 plus 4x2 bigger than or equal to 6, that's going to be replaced with x1 plus 4x2 minus x4 equals 6. And again, x4 is going to be non-negative. So this is the standard form of our linear program. The problem is, if we were to write this in tableau form, we wouldn't have any two columns that look like the identity matrix. So we wouldn't get an obvious choice of basic feasible solution. So instead, the idea is to apply the two-phase simplex method. And this is a clever idea. The idea is that to find a basic feasible solution, what we can do is solve a related linear program. And if we can solve that linear program, it'll give us the basic feasible solution to start off with. So we're actually going to apply the simplex method twice. Once to find our basic feasible solution, and then another time to optimize from there. Oops. Okay, so the idea of the two-phase method is to introduce two new variables x5 and x6 in this case. So we have one new variable for each equality constraint. So here we have two equality constraints. So we introduce two new variables. And what we're going to do is solve the following problem. So we're going to minimize x5 plus x6. So those are the two variables that we added. Subject to well, 4x1 plus 2x2 minus x3 plus x5 equals 12. So I added one of my new variables to the first constraint. And then I'm going to add the other variable to the other constraint. And also, we're subject to x1 through x6 are all non-negative. So what's the idea here? The idea is that if we have a basic feasible solution, or in fact, if we have any solution at all, if we have any feasible solution at all to the original linear program, well, then we better be able to find a solution to this program with x5 and x6 being 0. Right, because if we set x5 and x6 being 0, then x1 through x3 exactly satisfy the original equality constraints. So if we minimize x5 plus x6, if it's possible for them to both be 0, then they've both got to be 0, because that's the only way to attain the minimum of 0. Right, x5 plus x6 is going to be at least 0. The only way that it can actually be 0 is if x5 and x6 are actually 0. And also, if there was a feasible solution to the initial problem, then it must be possible for x5 and x6 to actually both be 0. Okay, so we're going to solve this linear program, and then the solution to this linear program will give us x1, x2, and x3, which form a feasible solution to our original problem. So there's a wrinkle here. What if we solve this linear program and we don't get x5 plus x6, or we don't get a minimum of 0? And then in that case, we conclude that the original problem was infeasible. Right, where infeasible means it's not possible to satisfy all of the constraints at the same time. So forget about trying to minimize your objective. There's not even a point that satisfies the constraints. Okay, so to recap, we added a dummy variable for each of the equality constraints. And what we did is we just stuck that dummy variable onto the end of each of our constraints. Right, and we remembered that we still have this constraint that all of our variables are non-negative. Okay, so let's go through how we would set this up with the tableau. So our first equation was 4x1, 2x2, negative 1x3, no x4s, 1x5, and no x6s. So maybe let me label these columns. And that sum was supposed to equal 12. And then if we look at the second row, well, we have 1x1, 4x2, no x3, negative 1x4, no x5, and 1x6. And that's supposed to give us 6. And now what's our objective function that we're trying to minimize? Well, our objective function when we're doing the two-phase method is we're trying to minimize x5 plus x6. So I have x5 plus x6, and then none of x1 through x4. Right, and I'll put a 0 here to start off. Okay. So this tableau is not in standard form. The reason that it's not in standard form is that we look at our columns that have an identity matrix, which is columns 5 and column 6, and we don't see zeros below those columns. So we need to perform row operations to move our tableau to standard form. So in other words, we want these two entries here to be 0. So how are we going to do that? Well, we're going to subtract the first row from the last row, and we're going to subtract the second row from the last row. that'll zero out these two ones in the bottom row. So the first two rows aren't going to change. But we can think of the bottom row, we're going to subtract the sum of the first two rows. So we're going to have a -5 here, -6, 1, 1, and then zeros here. And a -18 down here. So now we've got our tableau into standard form. Below this identity matrix, we have two zeros. So that means we're in standard form. Now that we're in standard form, these values across the bottom row are the reduced costs. So now we can just apply the normal tableau method like we're used to. So we look at the bottom row. What's the most negative entry in the bottom row, ignoring the -18? So -6 is the smallest guy. So this is the column that's going to enter the basis. Who's going to leave? Well, we compute 12 divided by 2 and 6 divided by 4. 6 divided by 4 is the smaller one. So that means we're going to pivot around this entry. So if we do the pivot, I won't do all the calculations carefully. I'll just copy it down, but we end up with this. So our second column becomes 0, 1, 0. That's what it had to be. And then when we perform this pivot step, we get this matrix. So let me separate out the bottom row to show that it's the reduced costs. Okay, so we still have negative entries in the bottom row. So the most negative one is going to be -7/2. So we look at the positive entries in that column. They're both positive. So we compute 9 divided by 7/2 and 3/2 divided by a fourth. Which one's bigger? Sorry, yeah. So we're going to pivot around the top right-hand entry of our matrix. This quantity comes out to 18/7. This quantity comes out to 6. 18/7 is smaller than 6. So that's why we're going to pivot around the first row, around an entry in the first row. So if we apply our pivot step, we're going to get 1, 0, 0 down the first row of the matrix. Then 0, 1, 0, -2/7, 1/4, 0, 1/7, -2/7, 0, 2/7, -1/14, 1, -1/7, 2/7, 1, and then 18/7, 6/7, 0. Okay, So it's not possible to reduce the cost anymore. And that makes sense because we see that the value of our objective function is 0. And we knew that our objective function was just x5 plus x6, and that can't be smaller than 0. Right, remember, objective function is the negative of the value in that corner. Okay, so this means that we've found the optimal value for this system that we created for the two-phase simplex method. And that's going to give us a solution to the original, or it's going to give us a feasible solution for the original problem. So if we look, for example, at what the basic feasible solution is here, basic feasible solution associated to this tableau is going to be 18/7, 6/7, 0, 0, 0, 0. So x1 and x2 are 18/7 and 6/7, and the other variables are all just 0. So how do I get a feasible solution to my initial problem? Well, I just get rid of x5 and x6. So the last two columns were the columns that I added just for doing the two-phase method. So I'm going to remove those columns. And make a new tableau. So this was phase 1 complete. Great. Found the optimal solution for the first phase. Second phase, we're going to remove these columns that we added. So we have 1, 0, -2/7, 1/7, 18/7, and 0, 1, 1/4, -2/7, 6/7. And now for the last row, well, our cost function is no longer x5 plus x6. If we scroll back up, the cost function that we cared about was 2x1 plus 3x2. So I'm going to do 2x1 plus 3x2. x3 and x4 don't factor into the cost. I'm going to put a 0 here to start off. Okay, so again, this tableau is not in standard form because I see an identity matrix here, and there aren't zeros below the identity matrix. So we just perform row operations to put it in standard form. So I want to zero out the 2 and the 3. So I'm going to subtract off twice of the first row and 3 times of the second row. So the first 2 rows aren't going to change at all. Great. And if I subtract off twice the first row and 3 times the second row, I end up in the last row with 0, 0, 5/14, 4/7, and -54/7. Okay, so now the elements in the last row are the reduced costs. So we notice that both 5/14 and 4/7 are positive. So both of our reduced costs are positive, and that means we're actually already at the optimum. So if one of those reduced costs was negative, then we'd have to chug along and do the simplex method with this matrix. But they both happen to be positive, so we can actually stop here. Okay, so the associated basic feasible solution Well, we see it's 8/7 in the first spot, 6/7 in the second spot, and zeros in the other spots. So, solution to the original problem is x1 equals 18/7, x2 equals 6/7, and the optimal value is 54/7. Right, so the minimum of 54/7 is achieved when x1 is 18/7 and x2 is 6/7.